If you have a set of data points on a flat, two-dimensional grid, they might cluster together very neatly. But as soon as that space expands to 3 dimensions, or 4, or 1,000, the volume of empty space grows exponentially. Points that were once close neighbors are suddenly pushed light years apart. In machine learning, this is called the curse of dimensionality. This creates a severe obstacle for empirical science. When we study complex systems, whether it's the stock market, the weather patterns, or human genetics, we tend to measure as many variables as possible. We gather hundreds or thousands of features, leaving us with datasets bloated by redundant metrics and overlapping noise. To make sense of this, we need to locate the hidden, simple relationships buried within that noise. We have to mathematically isolate the true underlying variables that actually drive the system. Massive datasets create severe geometric distortions. We need a systematic filter to strip away the excess and reveal the core structure. Imagine an idealized physics experiment, a ball attached to a frictionless spring. When released, this system has a very simple underlying dynamic. It oscillates back and forth, and its true motion moves strictly along a single horizontal line, a one-dimensional axis. Now imagine we are the experimenters, but we don't know this is a one-dimensional system. To be safe, we set up 3 separate cameras around the spring, pointing at arbitrary angles to track the ball's position. Each camera records a 2-dimensional projection of the ball, spitting out an x and y coordinate at every frame. Our simple one-dimensional physical reality has just been transformed into a convoluted 6-dimensional mathematical vector stream. This is exactly the problem principal component analysis, or PCA, is designed to solve. PCA finds an optimal change of basis. It performs a mathematical rotation of the coordinate system that collapses the redundant cameras and rediscovers that true one-dimensional axis of the spring. The algorithm starts with a simple translation. By calculating the mean of every feature and subtracting it from the respective columns, PCA centers the entire dataset exactly at the origin of our coordinate system. This chart shows fitting a line to a 2D spread to minimize orthogonal reconstruction error, the dotted lines connecting points to the green line. By minimizing this error, we simultaneously maximize variance, the spread of points along that new axis. This specific optimal line has a name. It is the first principal component. To find it, the algorithm computes the covariance matrix of the dataset. This matrix mathematically encodes how each variable fluctuates with respect to the others, giving us a precise measure of the data's orientation and spread. Extracting the defining characteristics of that matrix gives us our line of best fit. The first principal component is the primary eigenvector of the dataset's covariance matrix. But what about the information that first line missed? How does the algorithm capture the remaining variance? This chart shows the introduction of a second axis. To find the next component, PCA applies a strict mathematical rule. The second principal component, shown here as the orange line, must be perfectly orthogonal, or perpendicular, to the first. By locking these axes at 90-degree angles, these orthogonal eigenvectors construct a completely new, mathematically optimized coordinate system for the data. Each eigenvector comes with a corresponding eigenvalue, which tells us exactly how much variance it captures. By ranking them from largest to smallest, we establish a mathematical hierarchy that separates the heavy signal from the lightweight noise. Once we have this new coordinate system, we face a practical engineering question. Exactly how many dimensions do we keep, and how many do we discard? This Scree plot maps principal components on the x-axis against the percentage of variance explained on the y-axis. The first few components usually see a steep drop-off, capturing the vast majority of the system's structural information, often up to 86% in just 2 axes. Establishing this variance threshold allows us to safely delete the remaining dimensions. We can aggressively compress the dataset size while retaining its actual meaning. We can scale this geometric intuition up to a massive real-world example, the MNIST dataset, a collection of handwritten digits composed of 32 by 32 pixel images. If you unroll the pixels of a single 32 by 32 image, it forms an array of 1,024 values. Mathematically, that single image is identical to one coordinate point existing in a 1,024-dimensional space. When we apply PCA to this dataset, the geometry scales up. The principal components, the eigenvectors, are now 1024 dimensional vectors themselves. Because they share the input's dimensions, these eigenvectors can be reshaped and displayed as 32 by 32 images. In computer vision, these are called eigendigits. The first principal component captures a rich, discernible visual structure, broad strokes and common curves. But if you look at the 1000th principal component, it contains almost no variance. It is merely a single pixel of static. Dropping those later components is effectively a mathematical method for wiping away that static. It removes the friction of the real world, leaving only the true structural signature of the data. In practice, there is a critical, frequent engineering mistake made when using Python libraries like scikit-learn to calculate PCA reconstruction error. Applying the fit transform function does exactly what it says. It outputs the loadings. It maps the data into the new compressed feature space, transforming a large vector x into a much smaller vector z. Many developers attempt to calculate the mean squared error directly on these compressed feature space loadings. That is mathematically invalid. You are comparing points in completely different coordinate systems. To correctly measure the error, you absolutely must use the inverse transform function. This multiplies your compressed vector by the component matrix, projecting the data backward into the original high-dimensional signal space. True physical information loss is only measured by comparing your original signal to this reconstructed signal. Then you see exactly what the algorithm threw away. There is one final limitation to keep in mind. The PCA algorithm strictly assumes that the data exists within a linear subspace. This chart shows the classic Swiss roll dataset. It operates on a nonlinear manifold. The data curls back on itself. If you attempt a linear change of basis here, the projection collapses the structure, destroying the actual topology. PCA cannot unroll complex twisting geometries. It can only view them from different flat angles, mashing distinct layers together. Principal component analysis is an incredibly powerful tool, but it functions by strict mathematical rules. It remains a rigorous application of linear algebra to cut through the curse of dimensionality, provided you understand the geometry operating beneath the code.